We're very happy to have with us here today Dr. Srijit Paul from Maryland University. Srijit got his PhD in 2019 from Wuppertal University, and after postdocs in Mainz and in Edinburgh University, he's now a postdoc at Maryland University. He'll be here to tell us about thinking in a box, scattering particles to compute the structure of matter. Sorry about that. Yeah, go on, over to you.
Okay, so good afternoon everyone. Today I'm gonna talk about thinking in a box. On the contrary, people always encourage people to think out of the box, but today I'm gonna see what can we do if I just stay in the box and what all things can I explore. The theme would be I'll try to scatter particles in the box and also try to compute from that if it's possible to study the structure of matter and to be specific, maybe quarks and gluons and strongly interacting systems. So let me start. So this is the outline of my talk. I'll first talk about what does it mean to be life in a box, in the sense that in physics, box or studying properties of the spectra in a box is ubiquitous. Thanks. Okay. So I'll first try to. Oh, I just dropped it. Okay. Thank you. Yeah. So, yeah. So the plethora of avenues where we get to encounter a box, to be particular, I would say periodic box. And the question I will answer first is, how do I go about computing things in a box in general, from a very general perspective, without going into the specifics? And then why can I even compute things on the box? Like, what are the restrictions? Is it possible to get all the physics if I stay in the boundaries of my box or within the box that I'm talking about? And then after I define my conditions that I need to compute a quantity within the box, I'll try to first bottle up the strong force, and I'll see that if I put the strong force inside the box, what does come about it. I'll talk about protons, neutrons, and supercomputers that I compute and scatter in the box. And then using that, what are the different properties of the structure of matter that I can extract, especially if there are some complex structures which otherwise was inaccessible. Can I study them by studying them in a box? And then also a slight overview of some precision tests that we can come about by studying things in a box up till. So it has reached to a precision where I can actually compare with experiments and really give a run for money to them. Okay, so where all do we see a box or a periodic box? On the top left that you see here is basically a cosmological simulation where the box size, so I have kept the units in meters so that you can relate the scale of things that we actually use a box for in physics, right? For a cosmological simulation for large-scale structure of the universe, we have a box of size 10 to the power 26. And then, okay, this is a big jump, 26 to minus 6. So, and then if I go about cold atoms which are trapped in a potential, in this case maybe a harmonic trap, and that system is also studied, but this is of the order of micrometer, the box. And then we can also study electrons in a crystal, and the crystal being periodic comes a periodic box. And then in solid state physics, we have a box of 10 to the power minus 9 meters. And then slowly, if I come from electrons, atoms to nuclear, so say nuclear effective field theories, where I have a Coulombic term between the particles, and there I have a box of, say, 10 Fermi, or 10 to 30 Fermis. And then ultimately we can go down to subnuclear levels, where you have quarks and gluons as the degrees of freedom. And then we want to reconstruct the structure of matter using these basic building blocks. So box are really ubiquitous. So it's everywhere we come across. We use it in physics in different methods. And I will try to draw a unifying condition that unifies all these systems, maybe not the cosmology one, but at least the systems where quantum is relevant, quantum mechanics is relevant. Okay. So does everything reduce to a box, computing things inside a box? Let's see that. Let's try to answer that question. So here, if I start from left hand side where I want to scatter particles, and suppose I have this is the quantum mechanical system we all are familiar with. You have two particles, and there is a local potential of size x, and this is, for instance, one of the solutions of this. And then if I have such a problem at hand and I go about computing things, well, suppose if I cannot solve for the eigenstates of the Hamiltonian exactly, then I go about finding good basis operators where I can expand my solution to be. And that's when, so what I say, this is, for example, in 1D, a periodic box is essentially a circle. And the reason I'm talking about periodic box, because I want translation symmetry. So wherever I start on the box, I should get the same answer. So essentially what I'm doing is I'm taking the problem at hand, and I am finding a suitable basis, in this case a periodic circle, a circle basis. And then what I see, suppose this is the basis, and if I try to solve or try to represent my solutions here in this basis, and if these two particles are scattering, obviously the thing that we know very well, that if there is an interaction happening between the two particles within this finite regime of x, I'll see a phase shift happening in my wave function. So if the two particles coming from minus infinity to plus infinity, these two wave functions will have a relative phase between them, and that is basically, that will show up in the spectrum that you compute on the periodic basis, right? And so the only approximation here comes into is I have to have my range of my potential, or range of interactions in this case, to be much smaller than the size of the box that I'm starting with. So that's, if I have that in 1D quantum mechanics, this will help me encode the interaction within the discrete spectrum. Very simple. Now let's see an example what happens. So if I just take the 1D box and I take these two particles, of course, because of the interaction happening, there will be a phase shift. So because of the box, the momenta are discrete on this periodic lattice, and that's just 2 pi over L with an n integer. Then because of the interaction, there will be a shift, which is, so this is a very simple quantization condition that one comes about if I want to study this system. And depending upon the interaction, I will have an energy shift which is proportional to 1 over L cube, size of the box. And A1D is the scattering length for the 1D scattering length. And you can see that this, if the black line is the free energy, and then if you have attraction, then it will go down, and repulsion will push it up. Okay, 1D was easy. Let's, yes, correct. So that's the infinite volume quantity, and this is the finite volume quantity, to be specific. So this condition is somehow mixing these two things. So, okay. Now let's go to 3D. Now, of course, I don't have a circle anymore. I have a torus. And if I go about doing the same thing here, I also have 1 over L cube dependence, but in this case, this is scattering length in 3 dimensions. So note the units are different in this case because of 3-dimensional scattering length. And now see in 1D, the particle, when it sees the potential, it sees only a single number when it enters. So that's why you just have a single equation, and phase shift is just a number. But the moment you go to 3D, the particle, when it comes, it's looking at a 3-dimensional object or 3-dimensional interaction that's happening. So for the sake of brevity, let's just say I have a spherical symmetric potential. Then I know that if I'm on the sphere, I have 2 degrees of freedom, L and M, the angular. And that's why you have now your phase shift is not just a number, rather it's a matrix. And the whole condition that you had earlier reduces, or not reduces, say, expands to being a determinant condition. Because now you're setting that the wave function that is being felt when it is in the potential and it goes about, it should have the same form. So you take, you solve for the coefficient of the psi. So you have some kind of a function like a psi equal to 0, and then you want your solution to be unique. So you set the determinant of a to be equal to 0, and that's what comes about. And so, as I said from the previous equation also, this term has 2 terms. One is which mixes the local physics, right? The m infinity, which is in this case the scattering amplitude, you can say. And then you have a GL function, which is the cube geometry, right? And the only other assumption that I have here is, apart from locality, I have unitarity. It means the scattering that's happening, if it goes about, the probability is conserved in the whole torus, right? So just having these 2 assumptions, I can write down this quantization condition. And be amazed to see that this particular condition actually appears in all different areas of physics. So one equation but many dialects, you can say. So if I have this equation that I just showed you, determinant condition, if I just try to look at a system of cold atoms which are trapped in a harmonic trap, right? You can think of this as I'm just changing my basis from a box basis to a harmonic trap basis, and I do the same things that I did for the box, and I come across a formula which is given by Bush. I mean, people who work in cold atoms might know this. Bush formula is basically another form of writing this. So it's essentially the same thing. And then if I just go to condensed matter systems, as I said, electrons in a crystal, there is something called Lloyd formula, which boils down to this determinant condition where electrons are getting scattered. And another in the context of string theory and magnons interacting and spin-ons, this particular equation comes across as the asymptotic Bethe ansatz. And so it was fascinating for me when I first saw that, okay, I just did this one thing, such a simple setup, and it just appears everywhere in all different scales of physics that we do. And then, of course, in my domain with the strong force, where I scatter pions and strongly interacting particles, nucleons, and there it's called the Lucia formula. So this was a really fascinating find in the sense that this unifies not just strong force doing physics in such a short, small box, but up till maybe the micrometer boxes that are happening in the cold atoms. Feel free to ask any questions, and so. Yes, for sure. So what I mean is, when I have the particle that is coming in, and if I assume a spherically symmetric box, potential inside this, so it has 2 degrees of freedom, right? So it will, you can think of this as a matrix, right? And then if I equate the wave function that is being felt inside the potential and the one that's going round about the periodic box and again coming back to it, I will equate those 2 terms. So I'll get a matrix equation which is like some term A times the wave function equal to 0, and then that A will basically the difference between whatever is inside the box minus the one that comes all the way around. And then if I want a unique solution of that equation, the only way possible is if the determinant of that A is equal to 0. Yes, because the particle is going around the box, so it's feeling the cube geometry. Yeah, so basically this GL function will change depending upon the geometry that you choose to work with. For example, the Bush formula that you see here, it's not determinant condition anymore. It's basically a ratio of some gamma functions that comes in. So I'm not saying that the form will stay the same. This cube geometry will simplify your condition to some other form.
Then if the form changes, for example, as you just said, it's not the determinant condition.
Yes.
What is the common trait that you are going to work? Because after all, the form can be very different.
Yeah, the idea is I have a single function that connects finite volume quantity, in this case the cube geometry GL, the spectrum that I compute in finite volume, to something which is infinite volume, which is this scattering amplitude, which is just the potential. So I can get information from computing just something inside a box, and using this condition I can access infinite volume quantities. That's the idea. Okay, let's now bottle up the strong force. Now that I have a condition, a probe, how to study things in a finite box and how to scatter things inside a finite box, let's try to bottle up the strong force in this case. Now what do we have in the strong force? What are the ingredients that we have to work with? Well, we have 6 quarks and 6 anti-quarks, they're pairs. And here I just don't want to bother you so much numbers. I just want to give you the relative masses. I'll just give you the light quark mass, the up.
Sorry, I don't mean to.
Sorry, yes.
Just to come back to the point where is it roughly like saying that the number of arm states, for example, is
Levinson's theorem. It's related to that. But the point, yeah. But the beauty of this method is also not just bound states, because this M infinity that I showed, this contains information not just about the bound states, but it also contains information about resonances, decaying states, which are not part of the Fock space. Right. Correct. And the reason why we really want to access it, it will become apparent as I go about. In strong force, most particles are actually resonances. So there is no other way out. Okay. So essentially the ingredients that goes into bottling up the strong force are, we have from light quarks all the way till heavy, and these are 6 flavors that we have. And then we have a force carrier represented by the spring here, spin 1 particle. And each of the quarks carry color charge, RGB. That's just for the sake of simplicity to understand. We have represented them as colors. And the fact that makes QCD interesting and is the bound states of this quarks and the gluons, they combine to give you always a color singlet object which doesn't have any color. And no matter how, I have to always come up with something which does not have any color, to rearrange the quarks, rearrange the interaction between them, and end up in a colorless object. And we also know that bound states are inherently non-perturbative. One cannot really go about computing bound states using perturbation theory. One has to start off, like the first thing that we do in our quantum mechanics course is solving a hydrogen atom. You exactly solve the equation, you get the eigenstates, and then you do the perturbation theory for Zeeman effect and other perturbations or weak field that you introduce. So essentially you always have to start off, if there's a bound state in the system, you have to deal with it in a non-perturbative way. And the rules that govern the interaction between the quarks here are this Q cube. There is a term in the Lagrangian. I'm just not putting the Lagrangian up here. I'm just showing you there is a term which connects a quark-anti-quark pair. How does the interaction between the two quarks happen? And then there is a very important term which governs the interaction between the quarks and the gluons, which is weighted by a coupling term called G, which is the strong coupling coefficient. And then you have some self-coupling between the gluons themselves, which is given by this term. So what are the features of this strong force that we can use, that we have to be really careful about, is the interaction, the G that you saw, the G that couples between the quarks and the gluons is actually running. Now what do I mean by running? It changes with the energy that we are looking at the system. If I'm looking at scattering at a very high energy, so here is in log scale with 10 to the power 0, 1, 2. So if I am in very high energies, my coupling here is very small, and so what I plotted here is just the beta function, and coupling here is very small, so you basically have perturbation theory at your disposal, and you can actually just expand in your coupling in this regime. But if I'm trying to compute things at low energy, and if these particles that I'm talking about, this quarks and gluons, they actually combine to form hadrons in low energy, and they become the essential degrees of freedom at low energies. And in order to study these hadrons in this low energy regime, I need to deal with them in a non-perturbative way. And the most successful non-perturbative method that we know of which works is the lattice method. So this is just a description of how are you going to put these degrees of freedom on the lattice, and how does it look about. So you have the quarks at the vertices, and then you have the gluons which are carrying the interaction between the quarks, and you have the self-interaction between the gluons given by these plaquettes. And as I said, in low energies, these quarks combine with the gluons to give rise to particles called mesons and baryons. So these are both 2 quark or 3 quark objects, and if I want to study them on the lattice here, the reason why I mentioned that it's important to look at the low energy regime is because QCD is inherently not conformal. So I have to set a scale. I have to set my lambda QCD. So how does one go about? So the lambda QCD is set by fixing the lattice spacing. So this is essentially acting as a regulator, you can think of it. Think of it as a ultraviolet and infrared regulator. The lattice spacing is basically the UV regulator, because how close can you bring the quarks, right? You have to keep pushing a lot of energies to bring the quarks together, and higher the energy, it's in the UV regime. And then if I want to pull the quarks apart, take them away, long distance physics, that's infrared regime, and that's governed by the finite volume of the box. So there are 2 parameters here, which is the lattice spacing and the size of the box. That determines what physics you want to focus on. It's basically like a lens, right? There's a huge energy range, but I want to focus on this energy range, so I decide my size of the box accordingly. So a priori, before doing any lattice calculation, one needs to know what's the energy range I am looking at. And that's why I have to choose my lattice spacing and my box size accordingly. So basically these are the controls that I have, knobs I have. And then the quark masses are fixed by matching to the measured pions and kaons. Today's talk, I won't actually go into the details of how does one go about computing an observable on the lattice, because that essentially deals with some Markov chain Monte Carlo. But today I'm just gonna talk about, okay, the structure of matter right away from this. So until now things are pretty simple. You can think about quarks. Now let's see what are the complex structures from this simple quantities that can emerge, right? So let's see the complex structures. So this is the first thing that one goes about computing is the QCD spectrum, the hadron spectrum. And what you see here on the y-axis is basically the mass of the hadrons. You have mesons, you have baryons. And the blue dots are the particles that are computed and are used to set the quark masses, right? And you have this baryon that is being used to set the lattice spacing. And once you have, so basically that gives you a handle over the lattice spacing, and this energy range gives you a handle over the box size that I want to study in, right? So this was the first calculation that was done back in 2014, I think. And you can see that there are certain masses of the hadrons which are just very precisely computed, like the proton, for instance, right? And the lambda baryon, the sigma. But there are certain particles which have a width with them. The reason of the width is inherently the nature of the particle itself. Because back then when the calculation was done, it was essentially done at a much heavier pion mass, much heavier quarks. So this is essentially a world where quarks are very heavy. So these particles that you have here, they don't decay. They are stable particles, QCD stable particles. And if I look at the hadron spectrum from experiments in QCD, I have a very few number of QCD stable particles. And they are essentially, you have the pion, kaon, the proton. And then everything else that you see above is decaying to these particles back again. The question is now, if I do a calculation at an unphysical pion mass, these particles don't decay, but then if I take a continuum limit, would it be fair to take the number that I get out of it by taking the continuum limit or the infinite volume limit, and also the quark mass going to the physical quark mass limit, which is the chiral limit, would it be fair to take that number as the mass of the particle? Of course not, because that particle is decaying in the physical quark masses. So why do we basically settle with these big widths of particles? And that's where our formalism that we developed previously comes handy. The blue baryon? This is the sigma, right? This is nucleon basically. Sorry, I should have just been more specific about it. Correct. Yeah. Yes. Exactly. Eta prime. Yeah, that's a good question. I think so. This is not essentially my calculation, so I won't be able to comment on that eta prime. But eta prime actually is a topic which I think it's not a QCD stable particle, so it's difficult to compute using these conventional methods. Yeah, but the knife cock model, as you see, will. Yeah, we have to compute them. That's why the new method that we have, that I'm going to talk about, the same method that we just discussed, finite volume method, the condition, that will come in handy to compute the eta prime.
What I meant to ask is, in this work that you are, somebody else's work that you are reporting.
Correct.
Do you know whether they did discuss eta prime, or do you know why they excluded it? That's all I meant to ask.
I see. Well, at present, I have to really look into it. I don't remember it on top of my head. The only reasoning, whenever I have tried computing eta, or I know people who have tried computing eta, it's extremely noisy signal, and because essentially you're dealing with light quarks now. You're in this regime, right? And that gets very difficult. Yes. And eta.
Unrealistically heavy ion mass. What kind of number they use?
I think this was 700 MeV. So you can expect things are much different. So much, even eta will be a big thing to ask for in that case. Correct. Yeah. Correct. Yeah, basically, if you're in the, as I said, in the lattice, you have the Euclidean, the Wick rotation. So you don't have anymore the e to the power I et term. You have a e to the power minus e. Right? So if I don't give any momentum, that e becomes just the mass of the particle. Right? And essentially, when you compute the correlators at zero momentum, you end up getting an exponential decay function. And that's how you arrive. You just fit an exponential to that, single exponential to that. Exactly. You have to fit a window.
If they subtract out the constant decay, you get the one that will decay to the next one. That's how they
Yeah.
Is that right?
Yes. I have it all written up in the technical talk where I'm discussing everything in details, the exponential decay term, and how do we go about computing just the one that decays the slowest, essentially, right? That's the ground state, and I'm done with that. So, okay. So now I'll try to focus on the rho resonance, to be specific, because that's like the first light resonance that you see here. I'll see whether I can really compute it as a resonance on the lattice and not as a QCD stable particle. Yeah. If you do, then you don't see a plateau anymore because it decays. Particle decays. So the same thing, that's the correlator. If it is a QCD stable particle, the asymptotic state will be the ground state. But if the particle decays strongly, then you won't see asymptotic state at all. Correct. Exactly. So no, if it is a QCD unstable particle, then your whole idea is when you talk of an asymptotic state, you want it to stay an asymptote as t goes to infinity, right? But if that particle is a decaying particle and not a part of your Fock space of the Hamiltonian, so you have a decaying term which just gets you down. It doesn't stay in the Fock spaces. So the only way to deal with it, as you rightfully pointed out, is we have to talk about particles which actually interact to give rise to that state, right? Essentially, these are excitations of these stable states, right? I take the stable state, I excite it with a photon or another of the same particle, and then I get an excited state, and that's what. So basically, it's a multi-particle state, that decaying state. For example, the rho. Yeah, rho is basically 2 pions, right? So I cannot talk rho in isolation. And up till 2014 and all, this is 2011, I think. People were doing things in isolation, taking things as rho as the single hadron operator, and it has the quantum numbers of the rho, and that's what is set enough for them to work with and compute the rho.
Because like once you put the broadcast, the spectral is just the output of the light.
But you won't have the rho then, basically, because you won't see a plateau. So you will basically see, if suppose I am at the physical quark masses, right?
So but then I would say that that is the fate. Right?
Yeah, that's actually no-go theorem. It's called Maini-Testa no-go theorem, which says,
Why that's happening? I would have thought that what is the reason why it's happening? Because the lattices are supposed to like define set up for.
yeah, but if it is not a part of your Fock space, if that state does not exist as an asymptotic state, you are essentially creating it for a short amount of time and it goes away.
Oh, I see. So you're saying that because rho is an unstable particle genuinely gives you,
Exactly.
you're not actually exactly to see it in lattice. That's
You
what
not
you're really saying.
yes. If you start with only with physical quark masses. If you go to unphysical quark mass, correct. Correct.
Basically, like the mass scale you are shifting up so that the time scale for which the rho is giving is accessible to you in the lab.
Yes.
That's
Yes.
Yeah, I mean, now I understand.
You're pushing up your quark masses so that it decays slowly, slow enough that you can see the plateau and get the mass out of it.
But if one steps back a little bit,
Yeah.
before you even bother trying to identify with the resonance, maybe a more modest thing, say in the earlier era would have been to just identify rho as a particle.
But we cannot, right? If it decays, you can't really study them even in experiments. It's not something that you can detect. At max, you will see excess of pions at some energies. And then you infer that there must have been a bump somewhere in the scattering cross section, and that's the mass of the rho that you're coming up with. So essentially, if suppose I do not know the rho exists, and I don't know these heavier states at all, I just take the pion and the kaon, I keep scattering them off at different center of mass energies, right? At some point I will see a rho happening, right? At some point I will see that suddenly on the lattice, if I just construct 2 pions and I scatter them off, I will see an energy shift happening at certain energy between the non-interacting pions and the interacting pions, right? So if I start interacting 2 pions at lower energies, it will just bounce off like hard spheres, right? Nothing happening, elastic scattering. And then suddenly at some higher energies, I will see a shift in the energy, and that's the same shift. Not even scattering Lucier. If I just take 2 pions, if I construct the 2-body correlators, and then if I measure the energy in the framework of lattice QCD, and then the energy that I'll get by fitting the single exponential, that energy will be slightly lower than the non-netting energy. So that will basically give me a smoking gun hint that there is a form of interaction happening. And that's what essentially, so in the first slide when I showed you the delta E over L, you will see that shift. If the potential is attractive or repulsive, you will see that shift in energy. Yes. I'll go into the details of the energy shifts obviously in my technical slides, because there are a lot of things coming into extracting the energy shifts. So I'll talk about it in details, but the idea is once you have the energy shifts from this lattice calculation, you can plug it in to the determinant condition that I showed you, and that will basically convert the delta E energy shifts into the infinite volume scattering phase shifts. So what I show you here is essentially the experiments are the Estabrook and Protopopescu, which are this orange and the blue lines from experiments, and the blue points that you see, the dark blue points, are the results from a lattice calculation, the scattering phase shift from a lattice calculation. And you can see, and the gray bands that you see are essentially the resampling error for every point. So every blue point has a resampling error coming out of. And the slant in the resampling error is because of the cot delta that is there in the condition. The cot function is giving you a slant in the... No, they are from experiments. So that's why I see that you can see this, it just falls on top of. And this is a calculation done with physical quark masses. So that's the beauty. So now we are at a stage where we don't have to do any quark mass going to physical quark mass limit, no chiral perturbation theory. I don't want to offend anyone who does chiral perturbation theory, but lattice has reached to a point where chiral perturbation theory is becoming slowly irrelevant to take the limit. Obviously one can do a quark mass going to zero limit. That's again a part where you have to do chi-pt. Interesting anecdote is that when I was a grad student, my advisor Dina Alexandru in Cyprus Institute, I wanted to attend a course on chi-pt as a grad student. I told her, she said, oh, don't mind, in a couple of years you don't have to learn it because we will do everything in quark masses, physical. So and this is the value of the resonance parameters that we obtain. This is the PDG value, and this is our Bright-Wigner result from our lattice calculation. Of course the errors are higher, which means we need a more higher statistics, but at least we are in the same 1 sigma error. Okay, and another big recent discovery, would say, is the exotic structures that we see in experiments, in LHC-B for instance, where you have formation of this tetraquark-like objects. In this case you have 2 charm and you have D bar, U bar. Now this object was detected in LHC-B, and you can see the bump in the scattering cross section, and that's how they detected it. And on the lattice, people have been doing a lattice calculation at different pi mass here, and this is the 1 over scattering length, and this is the LHC-B value of the scattering length. And what we have achieved is we have also got in the continuum limit. If I take the m pi here to be physical, I'll be getting the LHC-B value. So this is a tetraquark object. So that's why this is exotic. So this, one cannot predict this from quark model. The naive quark model does not talk about objects having 4 quarks, 5 quarks, pentaquark objects, hexaquark objects. So it becomes difficult, and that's why lattice gives you that, because we can construct operators which has 4 quarks and respects the quantum numbers of the particle that we are trying to study here. Okay, and of course we have a big road ahead, and a growing list of hadrons being added every year by LHC. So these are all hadrons of this form, and you can see that there are 77 hadrons now at LHC which have been added, and it's a big task at hand to understand what's the point of having so many states, or say quark anti-quark, BB bar or CC bar or tetraquark states detected in experiments, and what can we say from first principles about these states? And I mean, these states are relevant in the sense that we don't know at the moment anything about these states, right? The only thing that we know that they have certain quark structure, and I know that which particles scatter off to give rise to these exotic states. But apart from that, I don't have any information about the structure of these states. How do they look like, and if they are deeply bound or they are resonating, they are resonances. So these things, these basically poles of the scattering S matrix, we have to track them down. How does the pole evolve as I reduce my pi and mass in my calculation? So there are new exotic states, for instance, 24 new exotic states. So because these states right now cannot be studied directly using quark model, we have to come up with lattice methods. And see, these 4 quark states could be that all these, they form a tetraquark, or they could form a molecule-like structure, which again is given by the Weinberg compositeness criteria. So one has to basically apply the Weinberg compositeness criteria to distinguish between whether it is a molecule-like state or is it like a tetraquark state. So it's associated with the, I think, the scattering length of the object that I'm dealing with. And so when I compute these things on the lattice, I have a overlap of my operator. How much does it look like a molecule state, and how much does it look like a tetraquark state, right? And that overlap factors along with the scattering length determines whether this is more like a molecule or this is more like a tetraquark state. Okay, and another of course, this is something already well known, that the mass of the universe, mass of the visible universe, for instance, the nucleon, is much heavier than the constituent particles themselves, as you can see here. So the proton itself is an emergent phenomena that's coming out of these light particles, the quarks, and it's a collective behavior of the quarks and gluons themselves that give rise to the proton. It's almost like in condensed matter, if you have a phonon in a crystal lattice, which is not a part of a Lagrangian, but it emerges. So you can think of it like that. So this is another aspect of the structure of matter itself that we can determine from using lattice calculations. And then this is another baryon resonance now. Now I'm moving up from mesons to baryons, where you have 3 quark objects. I think the color seems to be a bit off here on the slides, but the idea is what I'm plotting here, the mass of the delta and the nucleon with the pi and mass in the denominator, in the x-axis. How does my, if I change my pi and mass, if I go to all the way to the physical pi and mass, do I get a relation, a linear relation between these 2 objects? So there was a lattice conference back in 2005 where this calculation was also performed, where they were also computing the delta resonance, which is an excitation of the proton. But back then, because you can only do calculation at unphysical pi and masses where your delta is stable, so you have the points like this. You only have points like around 0.3 MeV, 0.3 GeV, 300 MeV pi and mass pions basically. So if I have 300 MeV pions, then I have a stable delta, and I really cannot compute my delta as a resonance. So you don't see any points after this here. What we have managed to do is so this will actually give us an idea of what happens if I change my quark mass to the physical quark mass. How does my pole structure change, right? Okay. We do see some complex structures appearing in QCD hadrons. Now let's move on to some precision observables that one can compute and maybe search dark matter. So this is again a famous G-2 that is, I think, already a hot topic this week. A lot of talks happening everywhere. So the idea, I actually gave a talk also in January about this. The idea is now this is an updated number of the experimental G-2 value, and this observable itself is an extremely important observable because it's a dimensionless quantity. It doesn't depend upon the parameters of the Lagrangian that you tune, and then you have this basically, to compute this to very high precision like this over here, you need to take into account QED effects, QCD effects, and the weak. And what you see here, obviously I'll go in a bit depth in the next week, in the next talk. So basically what we have is we have a new data from experiments for this, for G, and that has actually pushed the number. So this is the updated plot. So I just redid the plot from what was proposed last week in experiments and what was proposed by the theory lattice. So what you see here is basically, this is the red band, which is the experimental value, and it has the Fermilab 2025 numbers over here and the BNL numbers, and this is the world average of the experimental values. And the lattice calculation, so lattice here appears, let me go back to this slide. Here the uncertainty that is there in the HPP calculations and hadronic light by light, these are the two places where QCD interactions come into play. And this was actually the bone of contention between two approaches, that one is called the dispersive approach and one is called the lattice calculation, where I just compute this particular quantity on the lattice directly. And there is issue that they don't match at the moment. So the experiments, the dispersive approach has an experimental input, which is essentially a E plus E minus to hadrons data that feeds in. And right now, for example, these are the experiments that measured E plus E minus to hadrons, the green bands that you see here. So you have Babar, Chloe. The Babar and Chloe had already been quite far apart, which people were already contemplating that there is some issue with the data itself. And then the CMD3 came about last year, which mucked it up a lot. Now you see the dispersive approach, if I ignore completely the previous experiments, I get a value which is right on top of a lattice is proposing. But this has to be resolved in the sense that this is essentially very similar experiments which are measuring E plus E minus to hadrons, the R ratio, and they have to come up to a consensus between them that why certain experiments are giving a much lower value compared to CMD3. Oh, this is the lattice. Oh, this is the tau decay. Tau decay can also predict. That's not lattice. That's also experiment. So all the green bands are experiment, which are not the G-2 experiment, but an independent experiment. So exactly, this is the lattice. Yes. Correct. Now there are only two ways to go. Either they are wrong, or either he's wrong, or of course, there is something that they have to do and figure it out. Right now, we can only come up with scenarios if they are right, scenarios if this is right. Scenarios if this is right, then there is not much wiggle room for new physics to come in. Because then everything just fits in with the red band and you are essentially covered. it fits. And obviously I'll go into the details of the lattice calculation. Correct, CMD2 is somewhere here, yes. Yes. Yeah, I should have attended it. Yes, yeah. I know that there was a long list of around 50-60 questions sent to the CMD3 people about the experiment itself and the sources of uncertainties that can come up. Okay, so another avenue of precision test is the dark matter detection that is possible using lattice calculations. So right now the current setups that we have in experiments is basically a weakly interacting particle, dark matter, which is being scattered off a nuclear target. And if I'm looking at the properties of the dark matter itself, and if it is if it has to do with some nuclear effects, that is how it interacts with the nucleus or the proton, the nucleon, then, and if I assume that we have a spin independent interaction, there is no preferable spin or angular momentum to it, then it has to come up as a matrix element of the nucleon, the scalar matrix element of the nucleon, right, with that particular operator fed into it. So what I essentially mean is you have the scattering cross section, and this is the candidate that you can give me, or we can come up with together, something which is a spinless object, spinless operator, and then I compute this matrix element on the lattice using that object, and I can give you what is the scattering cross section for that particular interaction that we expect. So this is a scale of the detectors that we have right now. Yeah, that's a small human. So if you see that we are actually using xenon for detecting it, right? And xenon is like a very heavy nuclei. So essentially that also means that I can't just take a nucleon matrix element and be done with it, because we have a nuclei which has a lot of nucleons. So there are interactions between them as well. So that actually will also come up in your expansion of the scattering cross section as the second order term. So this can also be computed using lattice calculations, because n interaction itself is one of the major successes of lattice calculations, which you can compute a deuteron, for instance. So this is another input that a lattice calculation of this matrix element can give you as a dark matter candidate, if you want to compute, if you want to see whether what is the probability of such an event happening where you can detect an interaction because of the presence of dark matter. So what have we done till now? The structure of matter using lattice calculations have actually reached so this is some kind of a precision estimates at what all things have reached a certain precision. For example, G minus 2, for instance, that I showed you, and the mass of the QCD stable particles have already reached a precision of less than 1% from lattice calculations, which means these are like extremely sensitive to beyond and standard model physics that can come up. And right now the unstable hadron, for example the rho that I showed you, is still has an uncertainty greater than 1%. And then there is nucleon matrix elements from lattice calculations, which are still again in this domain, and this flavor changing neutral current B decays, which are also in this domain, and the CKM matrix elements are also known up till greater than 1%. And the tetraquark stuff that I showed you, which is basically heavy light object, where you have a heavy quark and a light quark in the same particle. That needs more refinement. It's still greater than 10% uncertainty. Okay, that's it for now. So I'll summarize my talk. So what I showed you is lattice calculations have actually reached a precision era, in the sense that I can compute things which are sensitive to new physics if it exists, and so it becomes relevant for all these experiments that you see here. LHC-B, the mu1 G minus 2, the Dune experiment, Atlas, and mu2, and the new hadrons that we detect needs to be understood. We need to understand them from first principles, because because there was a conjecture some point about the H dibaryon, which is a hexaquark object. It was conjectured by Jaffe back in 70s or 80s that it is a deeply bound object, and people started speculating that this could be a potential dark matter because it doesn't interact much with anything else. But then also recently lattice calculation found it to be just about bound with a very small binding energy. So it basically rules out such candidates that you can come up with as potential dark matter. I have to check, I don't remember at the moment. And also the periodic box that we started off with, right? We saw that it appears in all range of physics, right? From condensed matter systems to nuclear effective theory to quarks and gluons. And essentially the point where everything depends on is if I have unitarity and locality in my interactions, I can use a periodic box. And I can go about doing my calculation, getting an estimate for the spectrum non-perturbatively. And these conditions that we mentioned, nowadays there are a lot of calculations happening using quantum computers for scattering, right? And people are measuring entanglement entropy in scattering of pi. When there's a resonance, there's a sudden increase in the entropy. And what these conditions then can give you, so all these computations that happen on quantum computers, they have this issue that they have noise, right? And so basically if I have to come up with a smart way to mitigate that noise. And these conditions that I'm talking about, that we just discussed, can act as a verifier, which can act as an error mitigator for the estimates that will come up in such scattering calculations done on quantum computers. I think there have been active work happening about this. I don't know whether there have been 2 scattering papers from lattice community who have used this for error correction. Especially, I think Zore's group in Maryland is doing it. Yeah. Okay. So I'd like to thank my collaborators, which are all over. I have my PhD colleagues from ETMC Cyprus, from my postdoc colleagues in Mainz, Stuttgart, and these are the colleagues I have been working throughout from USA and Ulish. Thanks. I hope I'm on time. Correct. Good point. Yes, not just better computers. There has been so I think we should acknowledge, as physicists, there is a lot of development happening in the chip business, basically semiconductors, right? And all our problems that we see in our calculations are essentially matrix inversions or matrix vector products, which are extremely expensive, right? And all the chips that were existing pre 2007, or because there was a first paper in 2007 in the lattice community, which was called lattice QCD for gamers. And they were essentially using GPUs, which are not fast processors, but they are embarrassingly parallel, right? And that's what our calculations need. All the matrix or the linear algebra operations that we do in our calculations are memory throughput bound. They are not bound by how fast can you process information. It is bound by what's the rate of transfer of memory from my cache to the registers, right, to the CPU or the GPU itself. That is not fast enough. If I have that fast enough, I really don't need very fast 4 gigahertz Pentium processor. I don't need 4 gigahertz Pentium processor. I am fine with cheaper 700 megahertz processors like in GPUs, but I need a lot of them, which the GPUs are giving you. And essentially that's why now the calculations that are happening, if you look at the calculation that I did for the row meson, that actually was run on GPUs, and it actually won the Golden Spike Award in the Supercomputing Center because we were super efficient in using the resources. This was in Stuttgart, HLRS. Yes. Well, stay tuned. There are more details. What I showed you are the snapshots, because things will go deeper in the next talk as well. I'll go into the Thank you. Sure. Yes.